Okay, we're now ready to learn standing waves. Right now, standing waves are formed due to the combination or superposition of waves moving in one direction and then superposing or combining with the reflected wave. Okay, so in this case, let's say that we have a string that is attached at two ends. Okay, and if we were to cause a disturbance in this string, okay, either by plucking the string or by, say, bringing a tuning fork next to the string, that would lead to a vibration of the string. And if we were to do this, then what would happen is that there would be a wave that would travel in the string in one direction, okay, and then at the other end this wave would get reflected, and the reflected wave will combine, superpose with the original wave. Now what is observed is that for certain specific lengths, all right, certain wavelengths of the vibrations along this string, you have something called a standing wave pattern. Okay, and essentially when you look at it, you see that the wave it just seems as the wave is just there in front of you. Okay, the standing wave, we call it a standing wave. Now mathematically what is happening, and I don't want to go too much into the detail right now because I'd like to get the idea across first. What's happening is you have two waves moving in opposite directions and they combine, all right, and our conditions are going to be the following. So the different waves that you can get, okay, are going to depend on the frequency or the wavelength of the with which the vibrations exist in the string. Now what we know is that no matter what, at the two ends, okay, the points are fixed. All right, so nothing can happen. So we call these fixed points which have nothing going on, and call these nodes. Okay, now there is one pattern that we can have in the string which will look something like this. Okay, and it'll look as if it's just we call it a standing wave, because what will happen is in this particular mode of vibration, okay, there'll be a node once again in the middle. Okay, the points of maximum amplitude are called antinodes. Okay, and what happens essentially is that in this mode, each part of the wave is simply oscillating, okay, simple harmonically with this, with the time period and everything for the wave above its mean position. And when you were to look at this wave, and we'll demonstrate this in class, when you look at this wave, you end up seeing this pattern that seems to have just fixed in time. Okay, it's really cool to look at. But our goal is to figure out the conditions for what wavelengths will these things be set, and what are the different possible modes. Like I said, this is one possible mode, but are there other modes? Okay, so let's figure out what the different modes are in this case. Okay, and we call these different modes harmonics, and it depends on the length and also on the speed of the wave in the string. So if I have, let's say, the length of the wave of the string is L, okay, and let us say that the speed of the wave is V going through this, and we can figure V using this T square root of T over mu. Okay, then since we are restricted to having nodes at the end, okay, we could have a wave that looks something like this. Okay, we could have a standing wave that resembles this picture. We ask the following question: if this is the wave that is formed, what is the wavelength of this wave? Okay, the answer to that question is very simple. The wavelength of this wave is simply equal to, I'm going to call it lambda 1, and this is equal to, if you look at this picture, you see this is simply half a wave. So this will be equal to twice the total length of the string. Okay, we call this the first harmonic. Okay, because you cannot have a wave with a greater wavelength, okay, for this particular situation. It's not possible. Okay, because you have to have the two ends, nodes at the two ends, and so this is the longest possible wavelength that is allowed. Okay, so the V1 is equal to 2L, and once we know this, we can write the frequency as V divided by lambda 1. It will become V divided by 2 times. Okay, So this is the first harmonic. Now we ask, we can play the game, we can keep getting all our other harmonics. The second harmonic, on the other hand, is now going to have, once again, the two notes at the ends. Now we can add one more node in between. What we end up getting is something that looks like this. Okay. Now here, once again, the speed of the wave is the same, provided the tension and the mu are the same. We ask, now we call this the second harmonic. Okay, and we ask the question, what is the wavelength? In this case, the wavelength lambda 2 is equal to, if you look at this picture, it is the full separation, full L, okay, the distance between the things. And so we can write my frequency F2 as equal to V divided by L. Okay, and if you look at F2, F2 is nothing but 2 times F1, that is twice the fundamental frequency, which is the frequency for the first harmonic. Okay, this is also called the first overtone. Okay, the second harmonic or the first overtone. Let us look at the next picture. Okay, the third harmonic. In the third harmonic, once again, we will have the two nodes. Try to fill the gaps. Okay, so now in the previous one we had one node in the middle. Here we're going to have two nodes. So now my wave is going to look like this. It's going to go down, we'll go back up, another node. This is what it's going to look like. Okay, the length once again is L, and we ask what is the wavelength in this case. So this is our third harmonic. Okay, so my lambda 3 is going to be equal to what? Okay, so look at this picture, and you see that if I were to double my L, 2 times L would give me 3 full wavelengths. So lambda 3 is equal to 2L divided by 3, and this gives me my third, the frequency as V over 2L over 3, which is 3V over 2L, which happens to be 3 times my fundamental frequency. So if we keep following this, what we know is that the frequency for my nth harmonic is simply going to be equal to n times my fundamental frequency. So this is something makes life very easy. Look at the patterns and just prove to yourself that this is what you end up getting. Okay, or we can also write the wavelength for the nth one is going to be equal to 2L divided by n. Okay, see, for the first one we had, if you look at the first one, the wavelength was 2L divided by 1. The second one was 2L divided by 2. The third one was clearly 2L divided by 3, and then the nth one is going to be equal to 2L divided by n. So this way we can find all the harmonics, and we can figure out the whatever we need to figure out. We can get either the frequencies for the nth harmonic, or the wavelength, or the speed, or anything that we need to figure out. Okay, so this is basically stationary waves in strings.